Good morning. I am Kiran, student of Basic Chemistry Honors Final Year, Electronic Spectra. Introduction. It has been discussed in last chapter that when molecule absorb energy in the microwave region, far infrared region, transition between the rotational level take place, giving rotational spectra. Similarly, if the energy is absorbed in the near infrared region, transition takes place between the vibrational level accompanied by those in the rotational level, giving vibrational rotational spectra. However, if the light is absorbed in the visible region or ultraviolet region, electronic transition takes place, giving electronic spectra. A number of other processes also take place on absorption of light called photoprocesses. These may be photophysical processes such as fluorescence and phosphorescence or photochemical reactions. The branch of science dealing with such processes is known as photochemistry. In the present chapter, we shall take up a brief study of electronic spectra, where photochemistry will discuss in next chapter. Electronic transition and band spectra. The theory of electronic band spectra. Just as there are electronic energy level in an atom, there are electronic energy level in a molecule also. However, there are no simple formula available for the energies of these electronic levels except for hydrogen-like atoms. Electronic spectra are obtained when electrons in a molecule are excited from lower electronic level to higher energy level. However, as electronic transition is accompanied by vibrational and rotational transitions, the total energy of the molecule in any state is the sum of electronic energy, vibrational energy, and rotational energy. If EV, and ER represent the electronic energy, vibrational energy, and rotational energy respectively of the molecule in initial state before transition, and E dash, E mu dash, ER dash are corresponding value in final state after transition, then we have energy of the molecule in initial state E equal to EE plus EV plus ER. Energy of molecule in final state is equal to E dash E plus E dash V plus E dash R. Energy change involved in electronic spectra will be given by E delta E equal to E dash minus E. E dash equal to E dash E plus E dash mu plus E dash R minus EE plus E mu plus ER. Now final result will be del E plus del mu plus del ER. According to Planck's quantum theory, delta E equal to h nu is equal to h nu mu bar. H nu mu bar equal to delta E plus delta mu plus delta ER. Here the value of mu bar is equal to delta EE plus delta E mu plus delta ER at C for a particular transition, so that delta E remain constant, and for a particular vibration transition, so that delta mu remain constant. ER can have different value due to different rotational transition within the same vibrational energy change of the same electronic energy level. A number of closely spaced lines are also observed. This constitutes a band for each vibrational transition. Separate band will be obtained. Thus, due to different vibrational transition for a particular electronic transition of set of band is obtained called band group or band system. Each electronic transition will give a band system, hence the complete electronic spectra involving different electronic transition give rise to a series of band groups. Thus, the electronic band spectrum obtained for a gaseous molecule is quite complex. In spite of complex nature of electronic band spectra, these are preferred over the other type because these are obtained in the visible and ultraviolet region so that these can be easily photographed and studied. Calculation of dissociation energy of the molecule. A study of electronic band spectra reveals that at one end of the spectrum, the distance of separation between the lines becomes smaller and smaller till ultimately the line spectrum vanishes and space of continuous emission starts. The frequency corresponding to point where the line spectrum vanishes is the frequency necessary for dissociation of molecule into atoms. Thus, electronic band spectrum can be used not only for getting the information as given by a vibrational rotational spectra, but it can also be used in evaluating the dissociation energy of molecule. Potential energy curve and Frank quantum principle. The explanation of electronic band spectra and dissociation energy can be earlier understood in terms of potential energy curve and Frank quantum principle. The potential energy curve of a diatomic molecule is obtained by plotting the potential energy of system versus internuclear distance between the two approaching atoms. The curve obtained is all of the shape shown in figure 3.38. However, even at minimum energy position equilibrium position represented by point x, the atoms are vibrating so that internuclear distance keep on changing. Therefore, potential energy keep on oscillating about minimum position. The vibrational level thus occupied by the system may be represented by horizontal lines and indicated by approximate vibrational quantum number if sufficient energy is supplied so that system occupy the vibrational level represented by Vd. If corresponding internuclear distance should become infinity, the molecule should dissociate into atoms. However, this usually does not happen because before this stage is reached, the electron jump to the higher energy level. Electronic transition take place when dissociation will take place only of molecule in higher energy level. Now every electronic state has its own potential energy curve. Two such curves for the lower electronic states are shown in figure by 1 and 2 respectively. They differ in the fact that minimum of the potential curve for the excited state 2 is at larger internuclear distance than ground internuclear state. The dissociation energy of two states are different as shown in figure. D2 is less than D1. This is evidently due to the fact that bonding in the excited state is weaker than in the ground state. The vertical distance between the minima of two curves gives the difference between electronic energy of two states. The transition between two electronic states takes place according to the Frank quantum principle explained below. According to this principle, nuclei being much more massive than electron, an electronic transition takes place much more faster than nuclei can oscillate to change their internuclear distance. An electronic transition takes place from an extreme end of vibrational level from A or A dash as shown in figure 3.39. Because of velocity, vibrational energy of atom is zero at this position and they spend maximum time at this position. As internuclear separation remains the same, the transition can be represented by a vertical lines from point A dash to point C of the upper curve and not from potential energy minimum of lower curve to that of upper curve. The new vibrational level must be one which is nearest to point C. Counting lever, it appears that excited molecule will be third or fourth vibrational level of state 2. This explains why in the electronic transition there is no simple selection rule for transition among the vibrational level. All type of transition from lowest vibrational level to any of vibrational level of higher electronic states are possible. It may be mentioned here that according to quantum mechanics, the transition from lowest level takes place from the midpoint of vibrational level. This is equilibrium or the most probable position and not from the extreme position. The vibrational lever has large number of very closely packed rotational levers which have been shown in this diagram. Now, when the transition takes place from vibrational level to the electronic state of some vibrational level of upper electronic state, it is accompanied by a number of transitions between rotational level. The result is group of closely spaced lines called a since a number of vibrational transitions takes place. A group of band called band system obtained. Further, as transition takes place between many different electronic states, the electronic band spectrum consists of several band systems. Thank you.